Hi everyone. So in this video we introduce pooling and thereby basically finalize or complete all aspects of what a convolutional layer consists of. So typically the convolutional kernel is just what we discussed in the last video. This is just the first step of of what's typically called a convolutional layer. So a typical convolutional layer will consist first of a convolutional kernel that's basically doing the linear operation. And then there is a detector stage where you have the nonlinear activations and the same rules for nonlinear activations apply here, whether it's fully connected or a convolutional layer, which is basically these rules that it's desired to have non-saturating gradient and a consistent gradient direction. And then the third stage, which is the pooling stage. And pooling basically, as the name suggests, it refers to aggregating the output of many units or possibly many kernels, depending on how it is applied. Right, so this term here, nearby outputs, this is roughly, right? So it could be applied to nearby outputs. For example, you take 3 or 5 output units and aggregate their output to have only one unit, right? Or you could apply it over different kernels in parallel over different channels, right? So pooling forms a summary statistic of these units, of the inputs to the pooling unit. Now, there are many variations of pooling. For example, you could do max pooling. The maximum is taken as the output. You could do average of the input units. You could do the L2 norm or some kind of weighted average, right? So that all depends on the application. But in general, what pooling enables, so there is an obvious advantage, is that you can reduce the number of outputs of the layer, right? Because you are aggregating multiple outputs, but not necessarily that's not necessarily what you do with all variations of pooling. So in the next video we'll discuss the stride, and if that stride is 1, basically, so I'm taking the pooling over the first 3 over units 1, 2, 3, and then pooling over units 2, 3, 4, and then pooling over units 3, 4, 5. In that case, I'm not reducing the output units. So that's not the primary goal. The primary goal is to introduce what's known as invariance, right? So for example, if I introduce pooling over multiple output units that are nearby, then the output will not differ whether it's whether the change for small translations in the output units, right? Because I'm doing the same. So let's say I'm doing average over 1 to 3, right? It doesn't matter whether 1 equal 5, 2 equal 2, 3 equal 3, or if 1 equal 2, 2 equal 5, and 3 equal 3, right? So small shifts. So let's say I'm detecting the shape of an eye in an image of a face, right? If that image shifts by a little bit in terms of few pixels, right? And I'm doing pooling in space, right? Then I will have invariance to translation, to that small translation. And this is usually particularly useful for images because you don't usually want your detection performance to depend on the individual, to the sensitivity down to individual pixels, right? So because that will be dependent on the resolution, and in many cases it will not be perfect, right? Imagine, for example, I'm detecting edges, right? So edges basically are defined by corner points. So this line has to meet the other line at a pixel, right? Maybe they don't meet exactly because of the resolution, so they shift by 1 or 2 pixels. Then pooling make us alleviate or generalize well in these cases with these imperfect inputs. And note especially that invariance is different from equivariance, right? So we said convolution introduces equivariance, meaning if I shift the input, the output also shifts, right? But invariance meaning that small shifts of the input, the output remains the same, right? So in a convolutional layer, typically you would have both both properties. If you shift significantly, the output will shift with you. If you shift by a little bit, then the output will remain the same. So you have equivariance to translation because of the convolutional kernel, and you have invariance to small translations because of the pooling. Now, another very useful feature of pooling is that if you pool over the outputs of multiple kernels, so let's say I have in my layer more than one kernel. I have 3 kernels, and then I pool over the outputs of these 3 kernels, right? Then that could be very useful because the invariance now is not necessarily invariance to translation. In fact, the kernels will learn what transformation the invariance should be applied to. For example, let's say I have a handwritten recognition task, right? And then I rotate, so I have an image of a digit, right? I want to detect this digit, let's say a digit of 4, right? I want to detect this digit if it's slightly related like this, or if it's slightly rotated like this, or if it's like that, right? So maybe if I apply on three kernels and do pooling over them, right? Each of the kernels. So remember, you have convolutional stage. These are the kernels. Then detector stage, right? So let's say the detector stage activates when it detects a 4, right? So let's say that first kernel activates only if the 4 looks straight. The second kernel activates if the 4 is rotated by 45 degrees. The third kernel the detector stage for the third kernel activates if the 4 is rotated by minus 45 degrees, right? And then I take the max pooling over the output of the 3 kernels. Then what happens is that basically I am invariant to rotation by 45 degrees, minus 45 degrees, or 0 degrees, right? So when you apply the pooling, and in that example, max pooling over multiple kernels, these kernels learn what transformation by basically having diverse with respect, by basically being diverse with respect to that transformation. Here, rotation and diversity means that the kernels apply different degrees of rotation. The kernels learn which transformation the pooling introduces invariance to, and that could be very useful. And actually, mechanisms like that, learning which transformation to apply the invariance to, are what make basically are what's making convolutional neural networks generic, in a sense that the same network or the same architecture can be successful in very different applications. Thank you.